So welcome again to another episode of Shannon channel. Today I'm happy to have Jayadev Acharya from Cornell, and he's going to present an interesting talk on estimating symmetric properties of objects. So Jayadev, you're all ears.
Thank you very much. Thank you, Salim, for inviting me to speak on the Shannon channel. It's a real honor and a real pleasure. So I'll be talking about so let me try to share the slides, desktop. Okay, so are the slides visible?
Yes.
Excellent. So I'll be talking about estimating symmetric distribution properties, maximum likelihood strikes back. This is joint work with Hirakendu Das, Alon Orlitsky, and Ananda Suresh. And this talk will be primarily based on the following paper that appeared in ICML last year, titled A Unified Maximum Likelihood Approach for Estimating Symmetric Properties of Discrete Distributions. And I'll also post the slides online on my website, and I think probably the organizers will also post it on the YouTube link. So here is a brief outline of the talk. We'll first give some motivation for the problems. We'll look at some of the well-known methods and what the new approach is. We'll try to go over every proof if possible. We would want to understand at least some of the technical details that go into the arguments. And we'll close with some future directions. Please feel free to interrupt and ask questions at any time. And the problem will be simple enough that hopefully all of us can stay in sync until the end of the talk. Okay. So the first we will try to motivate the problem. So we are considering distribution properties. So what are distribution properties? So suppose P, this calligraphic P, it will denote a collection of discrete distributions. So what are some examples? One example could be delta K, which denotes the set of all discrete distributions over K elements. For simplicity, we just assume distributions over 1 through K. Okay. So one example could be delta 6, which is the distribution, which is all possible discrete distributions over 1 through 6. You can think of it as all possible distributions of a die, which can be loaded in very different ways. And we are interested in properties. So a property is a map from the collection of distributions to real number. So for every distribution, there is a real number. That's the property of the distribution. So for example, we may want to know what's the probability that a roll of a die will give you 3. Or we could be interested in knowing, is the dice actually fair? In other words, are each of the 6 sides equally likely or not? And we want to decide these things. And how are we going to decide it? So the framework is going to be the framework of property estimation, where P, we will assume that the source or the samples that we are observing comes from an unknown distribution from this collection calligraphic P that we know. And we are given independent samples from this distribution P. We are given n independent samples. And given these samples, the goal is to estimate the property f of P. So for example, we roll the dice a bunch of times. We may want to know what's the probability of 1/3. That will be the thing we want to estimate. Now, what does it mean to estimate? So in order to define it, we'll define the notion of sample complexity. It has 4 parameters, but I think it's pretty simple, so we'll pass through them. So it's the sample complexity S of a property F for a collection of distributions calligraphic P, and epsilon and delta are the accuracy and error parameters that we'll define as follows. So this sample complexity is the minimum number of samples that you need in order to estimate the function f of P up to an additive epsilon with error probability at most delta. So for example, if epsilon is, let's say, 0.1, and you want to estimate the probability of the symbol being 3, so you want to estimate the probability of 3 up to an additive plus or minus 0.1, with the probability of success being at least 1 minus delta. So the error probability is at most delta. And we usually assume that the error probability is a small constant, let's say 1/3 or 0.1. And the assumption is you can boost the error probability to any delta by repeating the experiment a few times and taking the median of the outcomes. Okay. So we'll be interested in symmetric properties in this talk. So symmetric properties are properties of distributions, or properties F, that do not change under permuting the labels of the input. So for example, the entropy H of P, summation P of X log 1 over P of X, it doesn't change if we permute the labels of the input from X to some other set. And similarly, the support size, it only depends on how many of the inputs have non-zero probability. So the support size of a distribution is the number of symbols that have a non-zero probability. And it only depends on what the set of, on how many symbols have non-zero probability. It doesn't depend on which symbols have non-zero probabilities. And there are many other properties such as Rene entropy. Support coverage is something that we will consider, all of which are symmetric. Let's take a couple of examples. So if you take a coin that has probability of heads 0.4 and another coin whose probability of heads is 0.6, both of these have the same entropy. Okay, and in other words, the entropy of a coin is going to be the same for both of these. Similarly, if you take a dice, and I'm going to erase all the 6 sides of the dice and relabel it in some other order. However, the mechanics of the dice stays the same, and therefore the output
Is everything okay?
Maybe the speaker was disconnected, so maybe we can stop and then see that we say.
Yeah. So
Hi, Jayadev.
Hello?
Yeah, Jayadev, what happened?
I don't know. So how long did I go? I thought I was just going.
No. You were disconnected for maybe 2 minutes.
Oh, okay. So where was I?
So you were talking about the 2-bias coin. Like you have a coin and you said if you relabel.
Yeah, you just relabeled the dice.
Yeah.
Yes.
So you were not disconnected on purpose, or?
No. It was. I didn't know I was disconnected. Aaron told me. Otherwise, I would have kept going. Okay. So is the slide visible?
No.
no, not yet.
Okay. I don't know what happened. Okay. Is it visible now?
Yes.
Yes.
And am I audible?
Yes.
You are very odd.
Excellent. So, okay. So I think I was here.
Yes.
Okay, so we said that symmetric properties are those properties that do not change under relabeling of the symbols themselves. Okay, and we said that the support size, for example, is a symmetric property because it only matters how many symbols have a non-zero probability. It doesn't matter what the names of those symbols are. Similarly, there is Rene entropy and support coverage. That's something we will consider soon. And if you take, for example, a coin whose bias is 0.4 and a coin whose bias is 0.6, both of them will have the same entropy. Okay, because if you take a coin and every time you see a heads, you are going to say, no, it's a tails. Or if you see a tails, you are going to say, no, it's a heads. So that's a relabeling of the symbols. And if the property doesn't change under relabeling of symbols, it's said as symmetric. Similarly, you could take a dice and you will scratch off all the sides of the dice and relabel it in any way that you want. And the symmetric property will not change under this kind of relabeling of the sides of a dice. Okay, so entropy is one of the most fundamental symmetric properties, and it's the central quantity in information theory. It's also one of the most popular measures of randomness of a distribution, and it appears as the fundamental limits of data compression as well as the capacity of channels. And the question we ask is how many samples are needed to estimate the entropy h of p up to an additive epsilon. And clearly, this is a simple question with many applications, and therefore there has been a really long line of work. And these are all the names that you can search each of them, and you'll find terms related to any of these methods, like Miller-Meadows method, jackknifed estimator, and so on. So why are people interested in estimating the entropy? So this has many applications. I'll just mention a few of them. So the first is to measure randomness in neural spike trains. You want to estimate how much randomness is there in the brain signals. It's also used in feature selection for decision trees, and also for it's one of the most popular methods for graphical model selection in an algorithm called as the Chow-Liu algorithm. And this is the tradition, and the following is the traditional setting in which this problem has been studied. And in fact, this is the setting in which most of the property estimation has been studied, perhaps a decade or before that. You assume that the underlying distribution comes from a discrete distribution over some set of k elements, and you assume that this k is small, like tossing a coin, rolling a die. And you obtain many, many samples from this distribution, and your goal is to then estimate this property f. So that's the traditional setting. But what happens with this modern applications or the big data setting is where, for example, in applications like genetics, neural spikes, or even text, computer vision, and ecology, is that the domain size k or the distributions could be over a really large set of elements. So k could be large, possibly infinite, or even be unknown, as we are going to see in the next few slides. So the question is, how do we solve the problems in the setting where the domain size could be really large? Okay. So let's look at one more problem that will also clarify where the distribution could be even unknown or the support size could be really large. So the problem is of estimating of the Courbet's butterflies. So Courbet was a very famous naturalist from Britain. He spent a couple of years, he spent actually 2 years trapping butterflies in the Malay Peninsula. And here is the table he came back after working for 2 years. Okay, this is his effort of 2 years. And so he obtained this table that has frequency and species. So the top row determines how many butterflies of a particular species did he capture. So this says that 118 species were so rare that he captured only one of them. And 74 species were a little more rare, but not so rare, so he could capture two of those species. And 44 species were such that he could capture 3 butterflies of that kind, and so on. So he came back and he asked the following question to Fisher. If I decide to go back to the Malay Peninsula for 2 more years, how many new species of butterfly can I hope to capture? So after looking at this table, you may say, oh, 118 species were rare that he caught them only once. So maybe there must be butterflies that he has still not seen. The question was, how many new species can you expect to see if you go back for 2 more years? Okay. So here is a formulation. Again, P will be an unknown discrete distribution. Let's define Sm of P as the expected number of distinct symbols that you can expect to see when you obtain m independent samples from P. Okay, so we can actually write Sm of P in a clean form. So Sm of P will be sum over all x's, 1 minus px to the m. So if you look at this expression in purple, it's 1 minus px to the m. It's the probability that when you obtain m samples from this distribution P, the symbol x does not appear. So 1 minus px to the m is the probability that the symbol x does appear. And therefore, Sm of P is the sum over all the symbols, the probability that they appear. In other words, it's the expected number of distinct symbols that you can see when you sample the distribution P m times. Okay. And you want to estimate SM of P even before you see M samples. So what's the goal? The goal is to estimate SM of P, and usually we are going to estimate it in a normalized sense, where you want to estimate SM of P over M up to an additive epsilon, but you want to do it without even seeing M symbols. Maybe you want to just see a real tiny fraction of M and then be able to say what's going to happen in the future. So for example, maybe you just see M over 100 samples, and then you want to be able to say how many distinct symbols you are going to see when you are going to sample M times. Okay. So again, just like entropy, there are many applications for this problem, including estimating the vocabulary size, measuring the ecological diversity, which is the problem of the butterflies that we saw, or even microbial diversity on skin. And this is a very well-studied problem, starting from from the 40s, 50s, and it's being studied even now. So Good, Tolman, and Efron and Thisted, what they showed is for a constant value of epsilon. In other words, if you want to estimate the normalized coverage, you want to estimate the expected number of distinct things that you see up to a constant factor, then you can do it by only seeing M over 2 samples. So in other words, if I see 1,000 samples, I will be able to say how many distinct symbols I'm going to see if I see 1,000 more samples. Okay, so in other words, if you go back to Courbet's example, after seeing the table for the butterfly distribution for 2 years, you'll be able to say what's going to happen for 2 more years by looking at just Good and Tolman and Efron and Thisted. However, it's not clear if Courbet actually asked Fisher, what will happen if I go back for 20 years or maybe 40 years? Can I know how many distinct butterflies I'll see from just the table that has measurements for 2 years? In fact, this problem was very recently solved by a couple of papers. The first one by Zhu, Valiant, Chan, that appeared in Proceedings of National Academy. No, this one appeared in Nature Communications. And then another paper by Orlitsky, Suresh, and Wu that appeared in Proceedings of National Academy of Sciences. Both of these papers show that by looking at only M over log M samples, so if N is M over log M, you'll be able to predict what's going to happen in M samples. So by looking at this tiny fraction, only 1 over log N fraction of the samples, you'll be able to say what's going to happen with M samples. And clearly, given the venues of where these papers were published, this is a very important problem with many applications.
Jayadev,
Okay.
I'm a little bit confused. Can you say it again, like repeat what the problem is again? I got confused about M and N. Oh, he got disconnected. So maybe Aaron can let him know. Try to talk to him.
What's the difficulty?
I think we lost him again.
Yeah, so Jayadev that got disconnected again.
Oh, okay.
I'll try to.
Raymond will go.
We lost you again.
Hello?
Hi, Jayadev.
Yes, hi. I don't know what's happening.
Yeah, are you? Yeah, this is the first time we have this. Maybe your connection or.
No, connection should be fine. I hope it's in Cornell. So, okay. Yeah, you had a question?
Yeah, so I think you did a nice exam motivation by Courbet, and then you gave him like a good numerical example, but I got lost in the end, the M and N. So
Okay.
because I feel like this is a fundamental problem. Like
yes, thank you very much for asking. Okay. So M is a parameter that's given to you. You want to be able to estimate how many distinct symbols you will see when you sample the distribution M times, but you actually don't get M samples. You want to do it without even seeing the M samples. You want to see the number of samples N that's much smaller than M and still be able to say how many distinct symbols you are going to see when you sample the distribution M times.
so what I sample is actually N.
Yes, what you sample is, so M is a parameter that's given to you. And the question you ask is how many samples you need you actually need to be able to say what's going to happen at m. You don't even need to see m.
Oh, okay.
So for example, Good and Tolman said that if I see m over 2 samples, so if n is m over 2, I'll be able to say what's going to happen at m.
With the constant epsilon and the constant is the error constant?
Yeah, the accuracy.
Oh, okay.
So if you want a constant accuracy, with half the samples, you'll be able to say what's going to happen in the future.
Oh.
And this more recent work, they showed that when n, the number of samples you get, when it's m over log m, when it's more than m over log m, you'll be able to say what's going to happen at m.
Oh. With also constant epsilon?
No, the epsilon will appear in the equations that we'll show soon. So this is for illustration purposes. This is for constant epsilon, yes.
Okay. And then
So for
right back to the example, the butterfly.
yes. Yeah, going back to the butterfly example.
So how does this apply there?
So in the butterfly example, what you're going to do is to look at the number of samples that you have, which is, so if you look at this table, yeah. So what you do is to count the total number of butterflies that you have seen, which will be n here. So that will be 118 times 1 plus 74 times 2 and so on. That's the total number of butterflies that you have captured, and that will be your n, the number of symbols that you have seen, okay? And this m over log m is going to translate into n times log n. In other words, with these n samples that you are seeing, I'll be able to tell you what will happen when you have n times log n samples. Okay, that's how it will translate. So you look at the number of total butterflies that you have, that will be your n. That's the number of samples you have. And now you can say what's going to happen at n times log n.
And how did you tie it to 2 for the next 2 years?
How does it tie to?
You said if he stays 2 more years, so that's like
that's like 2n. You hope that you will capture the same number of butterflies. Maybe then you will see a lot more repetitions.
All right, thank you.
Yeah. So the density of butterflies hopefully stays the same. Okay, so these are very basic questions. So how do people usually solve it? So what are the methods? The most famous and the simplest method is the plug-in estimation. And the way it works is the following. You get these n samples. So the first step is to obtain an estimate of the distribution itself. You obtain an estimate p hat for this distribution p that you don't know. And instead of outputting f of p, you just output f of p hat and hope for the best. Okay, so how do you estimate p? How do we get this estimate for p? How do we know what p hat is? The most popular estimation for p is what's called as the maximum likelihood estimator. We call it a sequence maximum likelihood. And the way it works is the following. You take the sequence that you see x to the n, and you find the distribution p that's going to assign the highest probability to the symbols that you see, to x1 through xn. Let's take an example. So suppose you toss a coin 3 times and you see 2 heads and a tail. What you want to do is to find the value of p of h that maximizes the probability of heads, and tails. Now, since the samples are independent, the probability of heads, tails is p of h whole square times p of t, the probability that you see 2 heads and 1 tail. And you solve this optimization problem, you'll end up with the following. You'll end up with the probability of heads as 2/3 and the probability of tails as 1/3. Okay, and this is a general phenomenon that the sequence maximum likelihood will be exactly equal to the empirical frequency distribution. Okay, so we need one notation. So let n sub x denote the number of times symbol x appears in x1 through xn. In the n samples that we have, suppose n sub x denotes the number of times x appears. Then the sequence maximum likelihood or the maximum likelihood distribution will assign probability nx over n to symbol x. So in the heads, tails example that we have, nh, the number of heads is 2, and nt, the number of tails will be 1, and small n will be 3, and therefore the probability of heads will be 2/3 and the probability of tails will be 1/3. Okay, so you do this once you obtain the n samples that you have. You find the maximum likelihood distribution or the empirical distribution and just plug in. So let's see how well it does for entropy. So people studied this as the first approach, and what they can show is that the sample complexity of this particular approach to estimate the entropy h of p over distributions of size k. So you have your calligraphic p is now the set of all distributions over 1 through k, and you want to estimate entropy of such distributions. So the number of samples you need to estimate the entropy of distributions using this method is going to be k over epsilon. So if you are interested in estimating the entropy for a constant value of delta, say let's say delta is 1/3, then the number of samples you need grows as k over epsilon. Okay, in other words, it's linear with k and inversely proportional with epsilon as expected. So if the domain size is large, you need more samples. If you want higher and higher accuracy, you need more samples. Okay. But it can also be shown that in the asymptotic of n going to infinity, SML is usually good. But with the large domain applications, and what we are interested in is looking at the sample complexity or the finite sample complexity bounds for these problems. And the sample complexity of entropy itself has been very well studied. And people now know that if you want to estimate the entropy of a distribution over k elements up to accuracy epsilon, the number of samples you need grows as k over epsilon log k. So this is a factor log k better than the previous, than the sequence maximum likelihood or the empirical method. And this is interesting. So for example, in the following sense, so imagine epsilon is a constant. Imagine epsilon is 1 bit. So you want to estimate the entropy to 1 bit. You can now do it without even looking at most of the domain. So you need to only look at k over log k of fraction of the domain, and you can still say what's going to be the entropy for the entire distribution. And this was obtained by a series of works, starting by the breakthrough result of Paninsky that showed that something sublinear is possible. So this is sublinear in k, in the domain size. And then Valiant and Valiant showed the dependence on k over log k. And in a couple of recent work that were published in the Information Theory Transactions, the final sample complexity was nailed down to k over epsilon log k up to constant factors. Now, of all of these works, the work of Valiant and Valiant is actually a plug-in estimator. They do give an estimator that first estimates the distribution p and then outputs a plug-in. But it has suboptimal dependence on epsilon. And a paper that appeared last week, I think on Archive, they claim to have an optimal dependence on epsilon that they obtained by tweaking the estimator that was proposed by Valiant and Valiant. Okay, so let's look at what are these optimal estimators that achieve this k over epsilon log k. How are these estimators? How do these estimators behave? So a general recipe that most of these estimators for most of the properties, including entropy, follow is the following. So you first estimate h of p or any function that you are interested in with a polynomial.
Nirmal just went over to tell Jayadev to call back in.
Sorry. So I don't know what the problem. This is the first time we have this problem.
I switched computers so that we could have a wired connection for this one because my office is quite close to Jayadev's, and I was worried that we had too many simultaneous streams going on, but that doesn't seem to have helped. There.
Yeah, is the slide visible? I don't know what's happening. Yeah, where was I?
I think, yeah, the Valiant and Valiant.
Yes. So we said that the Valiant and Valiant estimator is a plug-in estimator, but it has suboptimal dependence on epsilon. And there was a new paper that appeared last week on Archive that claims to have optimal dependence on epsilon that they obtained by tweaking the Valiant and Valiant estimator. Okay, so how do these optimal estimators behave? How are they obtained? So a general recipe for estimating any function that is followed in these papers is the following.
When you say optimal and epsilon, what do you mean? Like the
So the Valiant and Valiant showed that you can solve it by using k over epsilon square log k samples. So it's not optimal in epsilon. And here the dependence on k and epsilon both are optimal for these new estimators. Okay. A general recipe that these papers follow that obtain the optimal dependence on epsilon is first approximate h of p or any function that you are interested in with some polynomial function in p. And then just try to estimate that polynomial. And this general recipe requires a different non-plug-in estimator for each property that you are interested in. Like entropy will require something. If you want to estimate the support size, you'll require another estimator and so on. And they use sophisticated results from approximation theory that are beyond the reach of this talk. So if you combine all of this and look at the prior work in this field, people know what are the optimal estimators and optimal algorithms for various important properties. And a general result that follows is that optimal results are usually a logarithmic factor better than doing the empirical. So this is the example we saw. If you want to estimate the entropy h of p for distributions over k elements, then the optimal sample complexity is k over epsilon log k, and the sequence maximum likelihood requires k over epsilon. So from linear in k, you went to sublinear. Similarly, if we want to estimate the support coverage problem that we saw before, then the number of samples you require for optimal estimation is m over log m, the term we saw, times log of 1 over epsilon. And this is again optimal in both m and epsilon. And you can obtain similar estimators for both support size. So S of p was the support size of distributions. And the last one is the distance to a uniform distribution over k elements. And for all of these, people know what an optimal estimator is. So, okay, so all of this was known. So why are we doing and what are we doing? So what we show is a unified, simple, sample optimal approach for all of these problems, for all the 4 problems that we considered before. It's going to be a plug-in estimator. Moreover, it's going to be a maximum likelihood estimator. So in other words, we are going back to the maximum likelihood principle and solving the problem. Maximum likelihood itself has its roots of more than a century old. And we are saying that you can, in fact, use maximum likelihood. However, you have to use it in a slightly different fashion. So we were doing sequence maximum likelihood. Instead of doing that, we are going to do profile maximum likelihood, which we call as PML. Okay. So now we are going to look at what is profile maximum likelihood. So profile of a sequence is just the multiset of the multiplicities nx's that we saw before. So let's look at what the profile is with a couple of examples. The profile of heads, heads, tails will be 1, 2, denoting that there is one symbol that appears once and one symbol that appears twice. So you just write down the value of nx's of all the symbols that appear in a bag, and that's the profile that you obtain. Okay. Similarly, the profile for of length 4 sequence, where you see alpha, gamma, beta, gamma, is going to be 1, 1, 2. Implying that there are 2 symbols that appear once, and there is one symbol that appears twice. So this is the profile of a sequence, okay? And what's interesting is the following. Symmetric properties of distributions are determined only by the multiset of probabilities. It only depends on what's the probability, what are the probability values, P1, P2, and so on. It doesn't depend on what exactly are the probability value or the symbols themselves. So for example, a coin with bias 0.4 has the same probability multiset as the coin with bias 0.6. It's going to be 0.4 and 0.6. And for both of them, the symmetric properties are all the same. Yeah, so this is what I said now. So the probability of heads and tails, if the probability multiset for both of them is the same, which is 0.4 and 0.6, then they will have the same entropy, they will have the same support size, and so on. So an interesting result, which we are not going to show in this talk, is that profiles are a sufficient statistic for estimating symmetric properties. In other words, if I see heads, heads, and tails, or if I see tails, heads, and tails, my estimate for entropy should remain the same. Because it doesn't matter whether it was heads that appear twice and tails once, or tails that appear twice or heads once. For both of these sequences that have the same profile, I should have the same estimate for entropy. So that's going to be a critical thing for our approach. So this leads to the question of estimating the probability multiset itself, because if the multiset determines the property, it's sufficient to estimate just the multiset. And a maximum likelihood based approach for this was proposed by Orlitsky, Santhanam, Viswanathan, and Zhang in 2004 in a paper titled On Modeling Profiles Instead of Values. A longer version of the paper is available online. It's called On Estimating a Probability Multiset. And here is the approach they proposed based on, again, the principle of maximum likelihood. So in order to define profile maximum likelihood, we need to define what's the probability of a profile. So a probability of a profile, phi, is simply the probability of observing a sequence that has the profile phi. And then we just want to find the distribution that maximizes the profile probability. So we look at the set of all possible distributions in calligraphic P and find the one that maximizes the probability of phi instead of finding the one that maximizes the probability of x to the n of the sequence itself. Now this is the profile maximum likelihood. Let's look at one or two examples so that we are clear on what PML is. Suppose we see the sequence heads, heads, and tails. Then the profile is going to be 1, 2 as we saw before. Then what is the probability of the profile 1, 2? So the profile phi being 1, 2 means that there is a symbol that appears once, and there is another symbol that appears 2 times. All the sequences that have a symbol appearing once and another symbol appearing 2 times will have the profile 1, 2. We can write the probability of the profile phi as being 1, 2 as a sum of 3 different kinds of sequences, where the probability of P of SSD means that the first 2 symbols are same and the last symbol is different. Probability of SDS means that the first and third symbol are the same and the second symbol is different. And similarly, the last one means that the last 2 symbols are the same and the first one is something different. So by independence, you can write this as 3 times the probability of same, same, different. Okay. And you can expand to write it as 3 times the sum over all x that are not equal to y, P of x whole square times P of y, because you need to see one symbol twice and another symbol that's not the same as the last one. Okay, and if you look at the expression inside, it's a symmetric polynomial of the probability values. It's p square x times P of y. We'll come back to this in a second. So what's the sequence maximum likelihood probability for the profile 1, 2? So we know that the sequence maximum likelihood for this for the profile 1, 2 is 2/3 and 1/3. And you just plug it in the expression that we saw before. It's 3 times summation px square py, where x and y can have different, can be now heads and tails both. And you obtain that the sequence maximum likelihood probability for this profile is 2/3. Now, is this the best? Clearly, if we just wanted to maximize the probability of heads, heads, tails, we know that we should have
Aaron, do you know his phone number? Maybe I can text him whenever.
His office is like 2 doors down, so we just go pound on his door.
Yeah, I don't know what's happening.
I think it may be a good omen. So this gives them a small break. We can.
Yes. So where was I?
So the polynomials, and you are evaluating.
Go ahead.
But so you're gonna tell us. So this polynomial, there is a story where it comes from. Or,
yes.
Can I accept it?
What?
The polynomial.
Yes.
You're gonna tell us later how you came up with it.
No, so that's the optimization that we want to solve. So if you want to find the probability of the profile 1, 2, you want to maximize this polynomial p square x times P of y over all distributions. So recall that previously you were just trying to maximize one of these terms when you wanted to find the probability of the maximum likelihood distribution for HHT. You just looked at P of H whole square times P of T, right? Now you are saying that the profile could have come from heads, heads, tails, or from tails, tails, heads, or from any other thing. All you needed was for this profile to be 1, 2 is one element appears once and another element appears twice. So this is the probability of the profile. So the probability of the profile being 1, 2 is 3 times summation over all x and y, p square x times p of y. Okay?
Okay, yeah.
So then we looked at sequence maximum likelihood. So let's see. So previously we looked at sequence maximum likelihood for 1, 2 or for heads, heads, tails. And we saw that the sequence maximum likelihood was 2/3 and 1/3. Now, what is the probability of the profile 1, 2 under this distribution 2/3 and 1/3? So if you just plug in this expression 3 times summation px square py with the values 2/3 and 1/3, you'll end up with 2/3. So the probability of the profile 1, 2 under the sequence maximum likelihood distribution is 2/3. But is it the best? So the PML approach says that we should try to find the value of the profile phi, value of the distribution that assigns the highest probability to the profile itself, to the profile 1, 2. So in other words, you want to find the distribution P that maximizes the probability of phi. In other words, it maximizes the probability of summation p square x py. Okay, so this is the optimization we want to solve. Instead of one term of this expression that we did for sequence maximum likelihood, now you have all possible permutations of these things. And let's try to solve this optimization. So you want to maximize summation p square x times p of y. So you can write this as sum over all x's. So y is not equal to x. So you can sum over all y's that are not equal to x, and you'll end up with 1 minus p of x. So that can be written as summation p of x times p of x times 1 minus p of x. Now we know that x times 1 minus x, or r times 1 minus r is at most 1/4 for any r. And therefore, this thing in orange is always going to be at most 1/4. And the sum over x p of x is always at most 1. In other words, the summation is going to have value at most 3/4, and therefore the probability of the profile is going to be at most 3 times 1/4, which is 3/4, which is more than 2/3. So in other words, if we look at the profile maximum likelihood for 1, 2, we end up with something that's different from 2/3 and 1/3. We end up with something that assigns a higher probability to this. Okay, so this is the optimization that we solve. You look at the expression for sequence maximum likelihood, take all possible permutations and try to maximize it. Now, why is it even interesting, or what else can profile maximum likelihood do? So let's look at one more example. This is the alpha, gamma, beta, gamma that we saw. So there are 2 symbols that appear once and 1 symbol that appears twice.
One more question, maybe I got something wrong.
Yes.
Is it possible that your bound is
What do you mean?
Because you just did an approximation on px.
Yes. So okay, I see. So this is always at most 1/4, and you can achieve it by taking p of x equal to p of y equal to 1/2. So the PML distribution for 1, 2 will be the uniform distribution over 2 elements.
Okay.
So if you take p of x equal to p of y equals 1/2, then this is tight. Yeah, in other words, it's saying that the profile maximum likelihood for 1, 2 is not 2/3, 1/3. Instead, it's 1/2, 1/2. It's a uniform distribution over 2 elements. Now, if you look at PML for 1, 1, 2, which is alpha, gamma, beta, gamma, then it says that there is 2 elements that appear once and 1 element that appear twice. Interestingly, if you compute the profile maximum likelihood for this, you will end up with a uniform distribution over 5 elements. So what does it mean? It means that PML is able to somehow predict the existence of things that we have not even seen. We just saw 3 symbols, and we are saying if you want to find the distribution that maximizes the probability of this profile 1, 1, 2, you should have 2 more symbols that you have not seen. That's what PML is going to predict. And this is the optimization problem that you have to solve, and you can do it at leisure. I'm not going to go over it. Okay. The slides will be online, so this is a good exercise to do. So this is the method, and how does it work? So clearly, for it to make any sense, you need either plots or some justification. So here are the plots that were obtained initially by papers by Orlitsky, Santanam, Vishwanathan, Zhang, and Sajama, and recently Alan Pan. So what they did was following: take the uniform distribution over 500 elements and obtain 700 samples from it. Okay, and this red thing will denote how the samples will look like. So they took a uniform distribution over 500 symbols. With 700 samples, they saw three elements that appeared 6 times, 2 elements that appeared 5 times, 19 elements that appeared 4 times, and finally 118 elements that did not even appear. They took this profile and ran profile maximum likelihood on it, and they ended up with this green curve that looked much better than the red one. Okay, this is just one plot, right? So what they did was to run the experiment many more times, and almost every time they got something that was pretty good. Okay, so the question was, and therefore based on this, they said maybe here is a recipe to estimate any symmetric property f of p. You first find the profile maximum likelihood of the profile itself. So you take the sequence x1 through xn, the samples that you have seen, find its profile phi, then find the profile maximum likelihood, and then just output the property f for the distribution that you obtain. What are the advantages? It doesn't have any tuning parameter whatsoever, and it's not even specific to a function. So you obtain a generic method that applies to all possible functions that you are interested in. And beyond all of this, I think the strongest motivation is that it's rooted deeply in the maximum likelihood principle itself. Okay. So what do we show? We show that this method is going to be optimal for estimating a bunch of properties that we have seen before. So how do we go about proving that this method, for which we don't even know how to compute this profile maximum likelihood, how are we going to show that this method is optimal for estimating all the properties that we saw before? Okay, so in order to do it, what we are going to show are a couple of results. The first is how good is maximum likelihood in a general setting. Irrespective of what the problem is, we are going to state a general result for maximum likelihood that's going to hold in every setting possible. And then we are going to combine it with the second part of the result, where we'll prove strong bounds on error probability. So let's go into the first part. So here is a general maximum likelihood plug-in estimation problem. So as before, so consider P as a collection of distributions, but now it's over some abstract domain calligraphic Z, okay? And again, F is some property of the distribution that you want to estimate. And what you are given is one sample, small z from this capital Z, and you have to estimate F. So think of this calligraphic Z as being the set of all possible n-length symbols, maybe. So this is like one short coding for us. So you consider this abstract domain Z as the final set of samples that you are seeing. Okay? And you are given one such sample. So maybe this Z consists of the set of all symbols of length 3. So Z can be heads, heads, tails, heads, 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 and so on. So you obtain one such sample and you want to estimate some property of the distribution. So what's the maximum likelihood rule? It's going to be the following. So the first step is to take whatever this small z you have obtained. First, find the maximum likelihood estimate or the maximum likelihood distribution for Z. So it can be defined as the maximization over all distributions in calligraphic P. Find the distribution that assigns the highest probability to the symbol Z that you have seen. And once you have that, just output the function value at that at P of Z. So PZ of ML is defined as the distribution that assigns the highest probability among all the distributions in calligraphic P to Z. And you just output F of PZ of ML. Okay? So that's the recipe that we follow. Now, how good is this estimator in general? Is it a good estimator or no? That's what we are going to see. So the question is, how good is MLE? So the following result is a generic result on the goodness of maximum likelihood. So suppose F hat is an estimator for the property that we are interested in. So what we are going to show is if there is an estimator f hat with certain property that we are going to describe now, then maximum likelihood is going to be a good estimate. In other words, so suppose f hat is a good estimator. And what do we mean by good estimator? It's a good estimator if no matter what the underlying distribution P is, the probability that your estimate f hat is more than epsilon away from the truth is less than delta. So that's what we'll mean by f hat being a good estimator. So f hat is a good estimator if it estimates f of p up to additive epsilon with error probability at most delta. If this happens, then what we can show is that the maximum likelihood plugin estimator we saw before, the maximum likelihood plugin estimator will have an error probability, have an accuracy of at most 2 epsilon with an error probability that grows as at most delta times z, times the size of z, times how many elements are in this calligraphic z. Okay, so if f hat achieves accuracy epsilon, the maximum likelihood estimator will achieve accuracy 2 epsilon. However, the error probability can go up from delta to delta times z. Okay, so it's competitive with respect to the best f if we ignore this z that we'll come to in a second. So we are going to prove this because it's a simple proof. I think we can finish it in one slide. So take any distribution P in calligraphic P. Now define z bigger than or equal to delta as the set of all symbols, small z, to which P assigns a probability more than delta. Okay. Now for all the symbols that are inside this class, z bigger than or equal to delta, the claim is that f hat of z minus P of z is at most epsilon. Why? Because when the underlying distribution is P, then z is going to appear with probability at least delta. And whenever z appears, because it happens with probability at least delta, you must be able to estimate f of p with accuracy at most, with accuracy at least epsilon, because otherwise it's going to violate the condition here, the condition of the theorem. Because it has to have, because f hat is an epsilon estimate with error probability at most delta. Therefore, f hat of z minus f of p has to be at most epsilon. Now what do? You notice that the maximum likelihood distribution for z is going to assign a probability at least p of z by definition, because pzml is the maximum likelihood. It's the distribution that assigns the highest probability to z. And therefore, it must assign a probability that's at least p of z, which is at least delta. And now you apply the same argument as before for this PML, for the maximum. Hello?
Yeah.
Yeah. Can you see the slides?
You can see an infinite number of.
Okay, so where was I?
You are in the middle of the proof.
Yes. Okay, so let me just brush over the proof real fast. Okay, so take any distribution P. So z bigger than or equal to delta is the set of all small z's whose probability under P is at least delta. Now for any such z, when the underlying distribution is the small p, then we know that f hat of z has to be cannot be more than epsilon away from the true f of p, because otherwise it's going to violate the condition of the theorem that's here. Because when you sample according to p, z is going to appear with probability at least delta. And for that z, you must have an estimate that's at most epsilon away. Okay, and therefore, f hat of z minus f of p is at most epsilon. Now you look at the maximum likelihood distribution for z. By the definition of maximum likelihood, the maximum likelihood probability of z is at least the probability of z under p, and therefore it's at least delta. And therefore, f hat of z, now you apply the same logic as step 1 to this new distribution PML, PZML. And therefore, f hat of z minus pzml will be at most epsilon 2. And now by triangle inequality, what you obtain is that f of p minus f of pml under z is at most 2 epsilon. Okay, so this happens with probability 1. So for all the symbols small z, whose probability is at least delta, you make no error in terms of the maximum likelihood. So the maximum likelihood estimator is away from the truth by at most 2 epsilon. So that leaves us with the set of all symbols whose probability is at most delta. So the set of all symbols z whose probability is at most delta. How do we take care of it? So the probability of f of pml minus f of p is being at most at least 2 epsilon is at most the probability that you see a symbol inside z of small z less than delta. Because we saw that z bigger than or equal to delta, all those symbols have to have a distance of at most 2 epsilon. So the probability of making an error more than 2 epsilon is at most the probability of seeing a symbol inside z less than delta. Now that's going to be at most delta times the set of all, delta times the size of z. Okay, so this is the entire proof for the competitiveness of maximum likelihood. So how are we going to use this result? Okay, so here is a theorem. It says that if you want to estimate some property f over a class p up to error epsilon and delta, then the profile maximum likelihood will have the following guarantee. Why? Because the profile maximum likelihood will achieve. So now imagine the setup is the following. The script z or the calligraphic z set that you saw is actually the set of all profiles of length n, because that's what you are going to see to estimate a symmetric property. Now the set of all the size of the set of all such profiles is given by the absolute value of phi to the n. Now from the result that we saw before, we could conclude that if we can estimate f up to additive epsilon with error probability delta, then the maximum likelihood estimator applied to the profile again will have an accuracy of at least 2 epsilon. It's better than 2 epsilon with an error probability that will be at most delta times the size of the number of profiles. Okay, so what is the number of profiles? What's the number of profiles of length n? So each profile of length n is actually just a partition of n. In other words, if you look at all sequences of length 3, the set of all profiles can be written in the following way. Because all the 3 symbols could be the same. There could be one symbol that appears once, one symbol that appears twice, or there could be 3 distinct symbols. Okay, so the set of all possible profiles are in one-to-one correspondence with unordered partitions of the integer n. And therefore, the size of the number of profiles is the partition number of n, which grows as at most e to the power of 3 square root n. So it grows as at most e to the power of some constant times square root of n, the number of profiles. So, okay, I'll skip this argument, but maybe I'll just mention it in brief. So what we can show is using the argument in the previous slide about the number of profiles being e to the square root n, is that if the sample complexity of estimating f is n, then PML is going to estimate f with number of samples that's at most order n square. Okay, clearly this is a bad result in the following sense that we are requiring quadratic number of samples. So why is it even good? But this is a general result and it holds for every possible p. The way it works is you first take some n times L independent samples and divide them into L parts. And for each of them, you estimate f independently. And you take the median of these estimates. You can show that the error probability now drops down exponentially with L. This is called as the standard median trick. And then you use the fact that the number of profiles with length NL grows as at most x power of 3 square root NL. And therefore, the error probability of PML is going to be at most e to the minus L, which is the error probability for the second term, times the number of profiles that are there. So delta times the size of the number of profiles. So once L is more than N, the error will dominate the number of profiles. And using that, you can show this result. So the summary of this slide is for estimating any symmetric property, if the sample complexity is n, then PML will have sample complexity at most n square. Okay, but that's not good enough. So what we do is the following. So recall that we said that to estimate the entropy of a distribution over k elements up to additive epsilon and error probability 1/3, the number of samples was k over epsilon log k. Okay. Now let's suppose now what we do is to show that if you want to solve the same problem, however, with a much smaller error probability, what we were able to show is that, and this is the most technical part of the paper, is with twice the optimal number of samples, you can actually show that the error drops exponentially. In other words, the sample complexity of estimating entropy over the same set of elements and accuracy epsilon, with error probability instead of 1/3 being e to the minus n to the 0.9, it's still the same. It's still k over epsilon log k. So the error of estimating the entropy for the same accuracy drops down exponentially with just twice the number of samples. And this requires like modifying the existing estimators and obtaining some strong guarantees using McDiarmid's inequality. So we'll not go over this, but now we have all the ingredients that we need to wrap up the arguments. Okay, and we could show similar results for all the other properties that we discussed before. So this second result says that to estimate entropy up to additive epsilon requires sample complexity S for error probability 1/3. You can make the error probability e to the minus n to the 0.9, like something really tiny, with just twice the number of samples. So you have to do something better than just taking medians. And we are skipping over that. So now we can combine all the results. So there are two technical parts that we prove in the paper. The first is the following. That the number of, for all the properties that we have considered in this paper, like entropy, support size, and so on, that the error probability drops down from 1/3 to e to the minus 4. It could be n to the 0.8. I've written 4 square root n for some simplicity that will happen. That the number of if the sample complexity to estimate f up to accuracy epsilon and probability of error 1/3 is n, then with 4n samples, you can estimate f up to additive epsilon with error probability that goes down as e to the minus 4 square root n. So that's a very fast drop in the error probability. And we'll combine this with the maximum likelihood plugin result. What did that say? It said that if you can estimate f up to additive epsilon with error probability delta, where delta is e to the minus 4 square root n, then PML is also able to estimate f up to additive error 2 epsilon with error probability now delta times the number of profiles. Okay, so delta is e to the minus 4 square root n. The number of profiles was at most e to the 3 square root n, and therefore you can estimate f up to additive 2. Hello?
Yeah. By the
Okay.
way, Jayadev,
we have, I'll be done in 2 more minutes.
Okay, good, because I have also got.
Yeah, I don't know why. Yeah, this is terrible.
No, it's not bad. I think it's a good pause.
Yeah, maybe I just don't make a full screen. Will that help?
I think with 2 minutes, I don't know if we're going to be able.
Okay. Okay, let's see. Okay, so I just want to wrap up the proof at least, okay?
Yeah, sure.
So did I go through this slide?
Yes. Yeah.
Okay, great. So once we combine these two, we are done, okay? So yeah, now good. So we actually did the entire proof of the paper except for the technical part that I said. And it's a pretty simple paper, and what we tried to do is to show that maximum likelihood is good in a general setting if we just know that the sufficient statistic, or in this case, the number of profiles is small. Now we are going to wrap up with some of the open directions. Okay.
Jayadev, can you go back to the theorem we just proved?
Yes. This one?
So this is part of the proof, right?
Yes. Yeah, this is one. I didn't go over this in great detail, and this is the one of the main results. So you can estimate the entropy with an exponentially small error probability with just twice the number of samples. Okay, and we combined both of these to show that the sample complexity for PML is the same, is order optimal. It's the same as the best.
How about computational complexity?
That's the next slide. So computing the PML itself, we don't know of any simple way that provides guaranteed computation of PML, because it's a maximization of a symmetric polynomial. So it's somehow like maximizing a particular kind of permanent of a matrix. But there are some heuristics that have been proposed, like the EM algorithm. That's what was used in the slides that we saw before, those beautiful plots. And there has been some recent work of approximating the PML via Bethe permanents by von Tobel and Waterdka recently. And there was one more paper that appeared last year by Jiao, Pavlichin, Weisman that do a convex relaxation for the PML problem. And what they obtained are these plots. So at least we can show these plots that are taken from their experiments. It shows that compared to, so these are all the previously known estimators. Many of them claim to be optimal. We can see that the plots of profile maximum likelihood and approximate PML are both doing much better. So the first direction of the first problem is to obtain a computationally good estimator for PML. How do we maximize that symmetric sum that we saw? And maybe it's hard. So what we can show, and what we showed in this paper, is even if you can approximate PML, that's good enough. In other words, so this is one clean question, okay? I give you a value of beta, any beta less than 1. Let's say beta is 0.6. Provide an algorithm that's an e to the minus n to the beta approximate of PML. So in other words, it assigns a probability that's at most e to the minus n to the 0.6 less than the true PML value. And what we can show is, even if we can do this, that algorithm will also be optimal for the properties we have considered. So maybe doing this is enough. So that's one optimization problem that's open. How to estimate or how to approximate the PML probabilities. The second direction is how can we go about proving other properties? So the KL divergence is a natural extension of these properties in 1 dimension to symmetric properties in 2 dimensions. And there has again been recent work on trying to estimate KL divergence. And recently I wrote a manuscript on where we showed that PML is optimal for KL divergence estimation. And it required some arguments in higher order. Basically, you look at partitions over higher dimensions. Another question that's clean and open is, can we come up with independent proof techniques? So what we showed is maximum likelihood estimator is good, or PML is good when something else is good. So we took some other estimator that existed and showed that when it has a small probability of error, or when they have good properties, then PML has good properties. Can we show PML performance independent of other results?
Adam, what's the name of your student who we're...
It's Nirmal.
What's his name again?
Nirmal.
Nirmal, okay.
Nirmal.
Okay. He's being very... He's saving the day, but...
Yeah.
Hello? Yeah, I was in the second last slide.
Okay. Well, wait a minute. We got feedback here, dude.
Yes. That's good. I don't know what would have happened without that.
Do you want to use this computer?
I'm on the second last slide.
Okay.
Hello?
Yeah.
Okay. Okay. So I think I was here, right?
We can just see your face.
Yeah. Oh. So we showed that MLE is good when something else is good. The question is, can we show that maximum likelihood estimation is good independent of the existence of other results. Like is PML good without that PML is good without showing that in fact something else was good. And can we do something for continuous distributions? And finally, the biggest question would be to show that PML is optimal for every symmetric property. So to summarize, we consider symmetric property estimation, and we show that profile maximum likelihood is simple and is optimal. So this is the last slide. So Fisher said that, so this is in Fisher's word, he said that nobody has been able to show that maximum likelihood is best under all circumstances. Because maybe you are overfitting. In other words, your maximum likelihood estimator computed with all the information may turn out to be inconsistent. Maybe throwing away some information. So we threw away the labels, and throwing away a substantial part of the information may render them consistent. So we threw away the labels and we applied the principle of maximum likelihood. And what we obtained was consistent or was sample optimal. Thank you.
Yeah, thank you, Jayadev. We would have time for questions, but I would have to run. I have to run to my class. But thanks a lot. I think people who have questions can write in the comments on when the video is posted on YouTube. And thanks again.
Yes, thank you very much.